So we are going to start with the workshop, and the first presenter is Dr. Daofeng Mei. Meanwhile, you are starting with the presentation. I'm going to say that Dr. Daofeng Mei is a Marie Curie postdoc fellow. He's the main IP of the CLG project at the Insituto de Carboquimica of the CSIC. And he has been working on chemical looping for around 14 years, with a special focus on combustion, gasification, and reforming processes, with a broad spectrum of activities. In this process, the Marie Curie Action, he will focus on oxygen carrier selection, proof of concept, process simulation, and life cycle assessment. So, Dr. Daofeng, you can start when you are ready.
Okay. Thank you, Paco, for your introduction. Welcome everyone to this workshop, and welcome to my presentation. So I'm going to talk about my Marie Curie project, which is CLG G3 Valve. So in this project, we want to develop chemical looping gasification with microalgae for the third generation biofuels production. So this picture, it shows clearly the global temperature increase after the Industrial Revolution. In the last 10 years, I want to find a laser. Yeah. So in the last 10 years, the global temperature has increased, surpassed 1.5 degree, and this is happening already, like earlier than the estimated year 2040. And global warming causes catastrophic consequences such as Arctic ice cap melting, extreme heat, and sea level rise, and so on. So greenhouse gas emission is a main reason for the global warming. And this picture shows the contributors to greenhouse gas emission. So more than 70% emissions are from the energy sector. So decarbonization in energy sector is taking a heavy burden. Renewable energy is an ultimate solution for the global warming, and 29% of Europe's electricity are from renewable energy. And EU is aiming to increase it to 43% by 2030. So during this transition to a renewable world, clean technologies like smart grids, energy storage, and carbon capture and utilization and storage, or CCUS, are emerging. But combining CCUS and renewable energy can gain negative emission, which is in addition to clean energy. This project, CLG G3 Valve, is such project which combines CCS and renewable energy, because it uses the CLG to generate syngas and at the same time capture CO2. And this project also uses microalgae as the renewable energy source. Now here is a logo of this project, and this project is a 2-year European postdoc fellowship project. And for those who may want to know, the fellowship's objectives are to support researchers' careers and to foster excellence in research. This picture describes the process of CLG for the third generation biofuel production. The central part of is CLG, which I will talk in the next slide. And the project has advantages of combining CCS and bioenergy generation. And it can help to gain negative CO2 emissions, and it can help to generate high purity syngas, but with lots of dilution by nitrogen. And with this process, there is a very low risk of heat exchanger corrosion, and the system can operate under autothermal condition, but with the absence of oxygen. And tar formation in the process can be hugely surprised. So this we have a homepage of this project, which we made with the Google sites by ourselves. And it's very easy to find. If you are interested, you just need to search CLG G3 BIOF with Google, and you can find it is there. We also have a YouTube channel for the project. There are some videos about the project, but I didn't update it recently, but I can upload the current presentation afterwards. Before talking about CRG, I want to introduce first the chemical looping combustion, or CLC. CLC has two reactors and oxygen carriers that circulates between the reactors to transfer oxygen. So in the air reactor, oxygen carriers take up oxygen from the air, and in the fuel reactor, oxygen carrier provides oxygen for fuel combustion. So air and fuel are never mixed in the CRC process, and fuel reactor gases are only CO2 and the steam. Well, the CO2 is easy to capture after simple condensation. CRC happens when the overall oxygen to fuel ratio, that is a lambda, is higher than 1. And when this lambda is lower than 1, CRC is changed to CRG process. So CRG gasifies the fuel to syngas, which is then subject to CO2 removal and purification. And the purified syngas is an important precursor for many industries synthesis, like biofuel generation. So in addition to the current CRG3 BIOF project, other recent projects on CLC and CRG I would like to mention, which include the CHEERS project and Clara project. The CHEERS project is about chemical looping combustion, and Clara project is about CRG, the chemical looping gasification. Both projects ended last year, and we also have a new project on CRC, which is called BioFlex CRC. It has already started in June this year, and another project on CRG, Pago has just mentioned it is called Biomega Fuel. So it has started in the beginning of this month. This project has 4 work packages. The first one is oxygen carrier selection. The second is proof of concept. And third is the process simulation. And the fourth is life cycle analysis. In the first work package, we're going to use 2-step selection to select suitable oxygen carriers. The first selection is to use the batch reactor to select some candidates. For the second step, that we will do a further selection with a 1.5 kilowatt pilot in our group. In the second work package, I want to do some experiments with the 50 kilowatt in the lab to prove the concept. And the third one, we will do some process simulation, which is also called the power of silence, to explore the opportunities and challenges when integrating the CRG and G3 above to upstream, downstream processes. The last work package is to do life cycle analysis about all the stuff involved in the process. Maybe not only the process, but all the upstream and downstream processes. From cradle to grave, not only from cradle to grave, but maybe also from cradle to cradle. One question, maybe some people want to ask, why do you use microalgae? So there are possibly many answers. Here, it's just my thoughts. I would like to share. So, and first, because microalgae are biomass, and when used in CLG process, it means it has lactive emissions. And microalgae grew 30 times faster than other biomasses, and also they use very less land and water than other plants or crops. And the third is that the microalgae have low competition with food chain, and also have high value products extraction. For example, lipids extraction, the residue from microalgae is also biomass. So we can use microalgae and also residue from the microalgae. And microalgae can also be used in wastewater treatment. This is just one example, and it can also be used in other processes. So this can open an opportunity for us to integrate with other processes. And so more products come from one chain, one value chain. And CLG could be extremely suitable for microalgae. And the third generation biofuel production, it means better economic and environmental. And microalgae residues have high value product extraction, a large amount, and suitable techniques are needed to process them. And CLG could be one. With this project, now I want to start to share that what we have done. We done the first one. The first we done is the first step, oxygen carrier selection, which is designed for the first work package, and the second is that the TJ experiments for kinetics of char gasification. We got some data. So we used the batch fluid as bed to test the candidates, the oxygen carrier candidates. The batch fluid as bed has a gas preparation system, a high temperature stir reactor tube, a fuel feeding system, and a gas analyzer system. The microalgae are from Brazil, but when they are received, they are fines or powders smaller than 10 microns. This is a lot big, we cannot use this powder in our system. So before we use it, we graduate with a granulator and save to 200 to 400 microns. And we can see in this table, the algae has 63% volatiles and 11% fixed carbon. And for you to look, we use 2 grams microalgae for every test. We use ilmenite, manganese ore, which is called MNGB, and LD slag, iron sand as the oxygen carrier candidates. The ilmenite is an iron titanium ore, and the manganese ore is a manganese iron ore, where the LD slag and iron sand are industry and byproducts. And zirconia is also used as inert, either mixing with the oxygen carriers or just as bad for blank tests. One question is here, when we use oxygen carrier in CLG, the oxygen carrier can be reduced to different degrees. And the different reduction degree usually means difference in oxygen carrier reactivity. The difference in reactivity, however, could lead to different rates in gasification, and so the gas distribution and yield may be different. And with this in mind, we designed an experiment matrix as seen in this table. So the oxygen carriers are mixed with synchronia, but were reduced to 0.2 or 0.5 to maintain the available oxygen in the bed. This is to avoid or to rule out effect of available oxygen in the bed. And three temperatures, 850, 900, 950 were used in the tests. Here is a typical cycle, and this typical cycle has a first CO reduction, and then oxidation, and the second CO reduction, and then gasification, and then the oxidation. The first CO reduction is to reduce the oxygen, is to find a suitable time that can reduce the oxygen carrier to a certain reduction degree, or what we call oxidation degree. That means the degree of oxygen carrier of oxidation of the oxygen carrier. And this table gives an example of the reached oxygen carrier conversion degree, which are very close to the desired value 0.2 and 0.5. The time found in the first CO reduction is then used in the second CO reduction to control the oxygen carrier conversion degree. A microalgae injection starts just after this second CO reduction. And here, I mean, after a few injections, it happens the volatiles release, char gasification, so like this, and we divide the volatile release and char gasification with when the methane concentration ends. So this is to facilitate the analysis of this volatile release and char gasification. So to say these two steps. First, let's look at the volatiles. So A and B compare the volatile gases with compare the volatile gases with synchronia as bad and ilmenite as bad. So when using ilmenite, there's less hydrogen if you so when we compare the hydrogen, so here it has a less hydrogen than the synchronia bed, where the CO and methane are similar with the two beds. This means little of the volatiles have reacted with the oxygen carrier and could indicate the contact time between the volatiles and the bed is very short. Further, we use hydrogen because here it has a hydrogen concentration has difference for these two cases. So we use hydrogen concentration to compare the effect of oxygen carrier oxidation degree, or XOX, and the OC tab. So volatiles conversion is very similar for all the oxygen carriers. We will not discuss more on volatiles, but put special attention on the char gasification. So here comes the gasification results. So figure A is an example of gasification with synchronia at 900 degrees C. And the similar, the concentration of CO2 and hydrogen, they are quite close. So this is similar CO2 and hydrogen concentration, and the lower CO suggests that the water gas shift could be relevant because these are very close, and CO is very low. This means it could reach the water gas shift equilibrium. But this is expected because we use high steam concentration in the bed. And the gasification with oxygen carriers can be divided in two groups. So group 1 is ilmenite and the manganese ore, and group 2 includes the LD slag and the iron sand. In group 1, CO, CO2 is the highest, but in the group 2, hydrogen the highest. So you can see the difference. And the further comparison is in this figure D, and clearly LD slag and iron sand have a higher gasification rate than ilmenite and manganese ore, and all have a faster gasification than zirconium. Average gasification rate are plotted as function of XOX, and the lower lines, meaning the thinner lines, are the available oxygen in the bed. In the case of LD slag, iron sand, and ilmenite, when the oxygen carrier is more oxidized, so the higher XOX value means it is more oxidized. Oxygen carrier is more oxidized. So when the oxygen carrier is more oxidized, the gasification rate is higher, where the manganese ore has a opposite trend. LD slag and iron sand have the highest gasification rates in all the cases, although there are less bed oxygen available. And temperature increase leads to faster gasification, and the higher temperature, the gasification rates with iron sand and LD slag are much higher than the other oxygen carriers. And this slide compares the CO and hydrogen yield from gasification process. And with all the oxygen carriers at 3 temperatures. But again, the LD slag and iron sand are the highest, have the highest gas yield. One question may pop up, that is, we found the CO and hydrogen is higher when we use LD slag and iron sand, and I want to know why this happens. So one explanation could be the calcium's catalysis on gasification. So LD slag and iron sand have a significant amount of calcium. And actually, the LD slag particle is easy to break down, either in cold condition or hot condition. We find a lot of finds when we operate with LD slag. So when it breaks, there's a chance to form maybe calcium dominant particles or fines in the bed. And second, at high temperature, calcium may have a better mobility and it can transfer to the oxygen carrier surface. So like this, so calcium may be on the oxygen carrier particle surface, but we probably also have like a kind of free calcium dominant fines. So when it's in fluidized bed, I mean, it's bubbling fluidized, but it's not faster fluidized bed. So the particles, the char particle can be immersed in the bed. It can have a chance to contact with the calcium, and then the gasification is enhanced. A second explanation can be the carbonation reaction. So this reaction, so CO2 plus calcium oxide, we got calcium carbonate. Here is a picture of this reactor. In the main reaction zone or the bed zone, the temperature could not be low. It can be 850 to 950. That's what we want. This could not, so the carbonation cannot happen at such high temperature based on our thermodynamics calculation. But on the upper part of the reactor, the temperature could be lower than 800 degrees. But at this lower temperature, this carbonation can happen. A third could be the water splitting. This was found more relevant for LD slag. So you can see from this picture, with these figures. and iron sand when reduced oxygen carrier were exposed to steam before they start the fuel. So what's water split means steam plus iron, we got hydrogen. But anyway, LD slag and iron sand are promising to get faster gasification and same gas yield. And so they are selected for the next step test for project, a 1.5 kilowatt CSIC pilot. Another work I'm doing is the kinetics of char gasification, and this could be used in process simulation. So in CRG process, the char is generated rapidly when the fuel is fed at high temperature. And the char is faster, so the char is so-called fast char. So we want to get intrinsic kinetics of fast char and use in CRG process, or maybe not only for this process simulation, but it can be also for other models. The fast char of the microalgae is prepared with this fluid aspect reactor. I put the algal particles in a weird basket and immersed it rapidly into the reactor. And so the particle can be hit quickly and it devolatiles quickly. And after volatilization, so you can see the flames because the volatile is burned close to the exit of the reactor because we have some oxygen on the top. But the reactor was still a natural environment at 950 degrees. And after quick cooling down, we got a fast char. I crushed and saved the char and used in kinetics experiments. The kinetics experiments of char gasification was done in TGA, and 3 milligram particles were dispersed in the TGA basket. And the big metrics of TGA tests that were made and effect of temperature, gasifying agent, steam concentration and CO2 concentration, and effect of hydrogen and CO products were all considered. So around 160 TGA tests were conducted. These two figures present an example of char conversion data and effect of steam concentration and hydrogen concentration can be clearly seen. And with this TGA data, we can get the long-mu in cell wood kinetics parameters, like energy, apparent energy, and expositional factors. And we want to use this kinetics parameter to get accurate process simulation model for the project. Okay, that's all from my part, and thank you very much for your attention.
Thank you, Daofeng. I think there is no questions on the chat. I want to ask you your future work relate with the operation in continuous units.
Yeah.
Just you are going to test all the oxygen carriers in the small continuous unit, or not? Or
No. My plan from this bitrack test, I can rule out the manganese ore. So I'm not going to test the manganese ore in the continuous unit. As you can see, I have selected the LD slag and iron sand for the 1.5 kilowatt CRG unit. I'm going to use these 2 oxygen carriers, but also I want to use ilmenite as a reference material because we have a lot of, not only us and other organizations have carried out experiments with ilmenite. maybe it's a good idea to have a comparison and to understand. Maybe we can get more information. Yeah, that's my plan.
Okay, thank you very much, Daofeng.
Thank you.
If anyone wants more questions, have more questions, you can put on the chat and we will discuss in the panel discussion at the end of the workshop.
Also, maybe you can just speak up if you want to speak your question. Yeah.